Hello and welcome to Skeptics in the Pub Online. Closed captions are available in the menu below if you'd find that useful. My name is James and I'm coming to you from Bedford, the home of the science of flat Earth and the future home of the Garden of Eden. The pandemic stopped us going to the pubs, but it didn't stop us being curious, and so we made ourselves a virtual pub online, where we now have fortnightly talks from a range of speakers. And unlike the lockdown rules in England, the format of our talks hasn't changed in an arbitrary and baffling way. We hear from our speaker, we take a little break, and then we come back and they will answer the questions you will have asked by going to sitp.online/ask. Our speaker today is Dr. Muhammed, with a PhD from Swansea University. They are now a quantum physicist at CERN, where they study antimatter. An advocate for STEM education, he strives to make science accessible and enjoyable for students and the general public, working particularly on initiatives to improve STEM education for underprivileged and underrepresented groups. He's lectured all over the world, from Pakistan to Portugal, and now he joins us in the pub. So please welcome, go crazy in the chat, for Dr. Muhammed.
Thank you so much, James, for the introduction. So it's a really pleasure to be invited to speak for Skeptics in the Pub Online. And today I'm really happy to be talking about antimatter. So just as a beginning, a precaution, antimatter is sensitive to light and vibration. So please silence your phones and avoid photography if possible. So my name is Muhammed. I'm currently a postdoc at the University of Manchester, but I'm based at CERN in Geneva, Switzerland, and I'm working on the alpha experiment where we study antimatter. And the topic for today is too hot to handle, the science and technology of antimatter. Before I begin talking about antimatter, though, I want to just quickly elaborate on my journey. I was born and raised in Islamabad, Pakistan. And then I went to the US to Cornell University in 2007 to study physics, where I graduated in 2011. Then I went to Saudi Arabia, of all places, to do a master's at KAUST along this very beautiful Red Sea coast. And then eventually I came to CERN in 2013, where I continue to work right now in Geneva, Switzerland. I work at a factory. It's the antimatter factory, to be precise. And this is what the factory looks like on the inside. Even though you might think that it's some shiny antimatter in a glass, it's actually a bunch of wires and cables and hoses. But I'll talk more about that. Before we talk about antimatter, it's very important to know about minions. So maybe some of you have watched the famous animated movie, Despicable Me, and this is a scene where the minions are ecstatic about bananas. So we'll come to this later on, so please keep this in your mind. To answer the question, what is antimatter? We need to first answer the other question, the more fundamental one. What is matter? So if you know a little bit about physics, or if you know a little bit about science, matter at its smallest size can be decomposed into two families of particles, which we call the quarks and the leptons. And you may have heard of the most famous one of them, the electron. But essentially, both the quark and lepton families have 6 types of particles within them. And for the universe that we mostly know, just 3 of these 12 particles, the up quark, the down quark, and the electron, are what we essentially need to create most of the particles around us. And how does that work? Well, you can combine 2 up quarks and 1 down quark to create a proton. You can combine 2 down quarks and 1 up quark to create a neutron. And then together with the electron, you can create atoms. And then with lots and lots of atoms, you essentially make up most of the visible universe around us. So what is antimatter? In 1928, there was a famous British physicist by the name of Paul Dirac, and he was studying quantum theory and trying to combine it with Einstein's theory of special relativity. And when you try to combine these two, you basically are trying to say that inside an atom, an electron abides by the speed of light. An electron cannot have velocities faster than the speed of light. And once you merge these two, Dirac came up with this equation, which is now famously known as Dirac's equation. And when you solve it, you come up with two solutions. A positive solution, which very accurately describes the behavior of the electron inside the atom. But also he found that there's a negative solution, which initially in 1928 he thought it's unphysical, like negative energy or negative mass particles, they can't be real. So he just threw them out. But 1 year later, he came back and he said, hey, wait a second. This means that there is something out there that's exactly like the electron, but has some opposite properties. It must be the anti-electron. And just 4 years later, in 1932, Carl Anderson, an American physicist, discovered the anti-electron in a cloud chamber experiment. So he was looking at cosmic rays passing through his cloud chamber, and he saw tracks that were bending in the opposite direction than what the electron would have bent in. And that was the discovery of the first antimatter particle in the 20th century. So both Paul Dirac and Anderson received Nobel Prizes independently, not like nowadays where you have to combine them. And essentially from that discovery, we came to know that matter particles have twins with essentially the same mass but opposite charge and some other opposite properties. So in the matter world, you have an electron or a proton that we know most of. In the antimatter world, you have the anti-electron, which is positively charged. That's why it's called a positron. And similarly, for the proton, you have an antiproton, which is negatively charged. So in 1932, the positron was discovered. In 1955, the antiproton was discovered. And then the antiproton discovery led to another Nobel Prize in 1959. So you can see why I'm interested in antimatter. It has nothing to do with Nobel Prizes. Today, we know that for every quark and lepton particle, there is an anti-quark and anti-lepton particle, and they all have been discovered over the years. What that means is that for the antimatter particles, they essentially have the same mass as the matter particle. They have the same magnetic spin and other quantum properties, but they have the opposite charge. So what does that mean for neutral antimatter particles? So in the atomic world, in the matter world, we have the simplest atom that we know of, hydrogen, essentially a proton in the nucleus surrounded by an electron in the orbitals. And similarly, in the antimatter in the antimatter world, the simplest atom, neutral atom, would be antihydrogen, where you have an antiproton in the nucleus and a positron around the nucleus. But you have to also be careful when you're working with antimatter, because when matter meets antimatter, something happens. They annihilate, and they convert into energy following the rules of Einstein's famous equation, E = mc squared. So in this case, where a positron and an anti-electron annihilated, they essentially turn into two photons, two energy or packets of light that go in opposite directions. So if you ever encounter your antimatter self, please be careful. Don't shake hands with them, because you will annihilate. This conversion of matter and antimatter into energy, it brings up the question, how much energy is there in antimatter? And so in this chart, you can see the energy density comparison of antimatter. On the left, we have the chemical energy, basically fuel that we burn nowadays in our car or gasoline. It's essentially 10 kilojoules per gram. Nuclear fission, which in nuclear power plants is about 8 orders of magnitude more energy dense than regular fuel. And fusion, which we're actively working on in the physics community, is maybe another order of magnitude more dense in energy, but antimatter is even further than that. So antimatter, if we had enough of it, we could use it as a fuel to store energy in a very, very dense way. But there's a caveat here, which we'll come to. So how can we use energy from antimatter? Could we power starships, to go to the nearest star? You would need 1 ton to go to Alpha Centauri. Or, like the movie Angels and Demons, you could use antimatter to blow up the Vatican. You just need 1/4 of a gram. Are these realistic? Well, let's do some calculations. It takes 10 grains of anti-rice is about 1/4 of a gram. So if you annihilated 10 grains of rice with 10 grains of anti-rice, you would basically be annihilating 1/4 gram of each. You get twice the mc squared energy. And if you do the math, you basically get 45 trillion joules of energy. But how much is 45 trillion joules of energy? 1 kiloton of TNT is about 4.2 trillion joules of energy. So essentially, you're creating 10 kilotons worth of TNT. And if you compare this to the atomic bomb that was dropped on Hiroshima, which is 14 kiloton, you're essentially on the same order of magnitude. Simply by using a quarter grams of antimatter, you could be creating the same amount of explosive energy as 64 kilogram of enriched uranium in an atomic bomb. It is definitely enough to destroy the Vatican City if you were ever going to do that. But how long would it take us before we actually have an antimatter bomb? So in this, we need to take into consideration the time and cost of producing antimatter. Currently at CERN, we produce about 30 million antiprotons every 2 minutes. And if you want to create a quarter of a gram, we just need to wait, do some math, about 20 trillion years. And I'm sure nobody is willing to wait for this long. So antimatter is definitely not a viable weapon. And at the same time, sadly, antimatter is not a future energy source because it just simply takes too long to accumulate enough, and it's too complicated and it's too technical. So what can antimatter actually be used for? You might wonder. If you cannot weaponize it, you cannot create energy from it, is it any use? Well, definitely yes. The first one is positron emission tomography. You might have heard of PET scans. The P in the PET scan is positron, which is the anti-electron particle. And essentially what you do is you take a glucose solution where some of the ions are tainted with a radioactive substance that emits positrons. So when you take the glucose solution with a radioactive isotope that emits positron, it goes to the parts of your body that are extremely active, like your brain, your heart, and also cancer cells and tumor cells. And when when you lie down inside this PET detector, essentially your positrons that you're emitting, they annihilate with a nearby electron in the cells of the tumor, and they emit the 2 photons, the 2 packets of light, which is detected by this detector. And then by simply having the patient inside this detector, you can create a 3D image of the active tumor cells inside your body. So it's used effectively for diagnostics, and it's been used for a long time, and it's in hospitals pretty much in use every day. The second use of antimatter, which is proposed, is antiproton radiation therapy. So at CERN, there was an experiment called ACE, the antiproton cell experiment, and they were trying to study how effective would antiproton therapy be compared to regular proton therapy or regular radiation therapy to treat cancer. And preliminary studies that were done on hamster cells, because we can't test on humans, preliminary studies showed that antiprotons would essentially be 4 times effective for the same kind of dose that we currently get with protons. The ACE experiment completed nearly, I think, 10 years ago, and the feasibility was proved. The issue with antiproton therapy is that it's extremely, extremely expensive to produce antiprotons. So right now, we're on hold, but maybe once we have more funding and once we have better technology to create antiprotons more cheaply, the study to use antiprotons for radiation therapy can continue. Yeah, antiprotons are 4 times as potent, but it'll take maybe many, many years away before we have clinical trials. For me, the interesting question is, can we use antimatter to solve some of the puzzles of the universe? And here's the puzzle. Annihilation of antimatter is symmetric. It's like a mirror image. What that means is that when you produce antimatter from E equals mc squared, essentially you get, for every particle of matter that you produce, you also must create an equal and opposite particle of antimatter. So if you have an electron produced, you must also produce a positron. And so you must have this pair production process. And we see this all the time in our labs. But we also know that the universe started from the Big Bang. A tiny size of the universe started from a lot of energy. And so we should have created from the beginning equal amounts of matter and antimatter. And they should have been continuously annihilating with each other and then recreating in this pair production process. And the universe would have been in just continuous flux where nothing like us would exist. But when we look out in the universe, we look around us, we exist, which means that there is no antimatter around us to annihilate with us. And actually, it gets much worse. The fraction of antimatter in the visible universe currently is essentially 0. This quote attributed to Einstein basically says that for every billion particles of antimatter, perhaps there was 1,000,001 particles of matter out there. And the billion annihilated, and basically what we're seeing currently is when the annihilation was complete, 1 billionth remained. That's our present universe. So it's very important for us to investigate the antimatter world. Scientists like myself, like others, are looking at antiparticles individually, like the positrons and antiprotons, but we're also looking at the more complex antimatter systems like antiatoms. And we need to really determine what, if anything, is different about antimatter. Why is there so much more matter in our current universe than antimatter, even though the production process and the annihilation process are symmetric? So we begin with the simplest antiatom. For matter, we have hydrogen, as I mentioned before, a proton and an electron. For antimatter, we have antihydrogen, the antiproton and the positron. So why is antihydrogen so important? It's the only pure antimatter system. Both the antiproton and the electron are antimatter particles. Secondly, we know that antihydrogen is neutral, so it's easy to control. And finally, we can do high precision comparisons with hydrogen, which we've been studying for more than a century, essentially. So how do we start? We have to make some antihydrogen. So you need to first create the ingredients of antihydrogen, the positrons. The positrons you can get pretty simply. You can get beta, you can get a radioactive source. In our case, we have sodium-22, and it has a radioactive decay channel called beta plus decay. So beta plus is essentially another name for positron. It decays into neon and a positron particle. For antiprotons, it's more complicated. The reason why we're at CERN is that antiproton production requires high energy collisions in a particle accelerator. And CERN has some of the best particle accelerators in the world to produce antiprotons. Where in the world can we make antiprotons? Currently, at the antiproton decelerator at CERN. In the past, there used to be the antiproton accumulator at Fermilab, which unfortunately stopped working in 2011. It completed its lifetime. And now there is another idea to make another antiproton factory, essentially, in Germany at the Fair GSI complex. But this is still a few years away. We think by 2028, 29, it will stop working. So currently, CERN is the only place in the world where we can produce antiprotons and study them and make antihydrogen. Where do antiprotons come from, you can ask. We need energetic protons to create a proton-antiproton pair. How does that work? You basically crash a beam of protons onto a metal target, and all kinds of other stuff comes from this collision on the other side. Some of the stuff that comes out is antiprotons, and we select antiprotons with a very specific energy and a very specific velocity using magnetic fields, and we extract them. Once the antiprotons have been extracted, they're still moving very close to the speed of light. So we need to first inject them into our decelerator. Then we need to slow them down. We need to cool them. We need to decelerate them. And finally, we need to re-extract them into our experiment where we can actually slow them down, trap them, and then study antiprotons and also potentially make antihydrogen from antiprotons. How do we hold something like antiproton? What do we need? The first thing we need is magnetic fields. When you have a charged particle like an antiproton, it essentially moves and rotates around inside a magnetic field in our trap. But we also need electric fields, because in order to trap the antiprotons axially, you can only use electric fields to trap them. So with the combination of magnetic and electric fields, you have antiprotons and positrons essentially trapped inside your trap. So the red ones here are the antiprotons and the green ones are the positrons. And then you can slowly merge them by changing the electric fields so that they come very close to each other. And eventually, if the antiprotons and the positrons are moving slow enough, some of the positrons will be captured and you will have a neutral antihydrogen produced. Now remember, we were using electric and magnetic fields to trap the antiprotons and the positrons, but atoms, like antihydrogen, are neutral. So as soon as they're formed, they basically drift to the walls of the chamber where they meet a matter particle, a proton and electron. They annihilate, and the annihilations are detected by our detector that surrounds the trap. So essentially, as soon as we create antihydrogen, it annihilates, and we know we had created antihydrogen, not that we have it. So we need to now learn how to trap atoms, neutral atoms. And the key feature we need to understand here is that atoms are also like tiny magnets. They have a magnetic spin. They have a north and a south pole. And similarly, both the antiproton and the positron have a north and south pole. The positron is the dominant one, is the bigger magnet here. And just like you can suspend things like frogs using strong magnetic fields. You can suspend hydrogen atoms or anti-hydrogen atoms using strong magnetic fields. So this is what we do in alpha. We merge the antiproton that we have inside the positron cloud. And when the merger happens, the antiprotons enter this cloud of positrons. Two positrons maybe collide or interact nearby. One positron takes the excessive energy, and the other positron is captured next to the antiproton. And this is essentially the anti-hydrogen atom that we've created. So anti-hydrogen production has a really interesting history, and we go through a quick history lesson here. The first anti-hydrogen was created at the Lear facility at CERN, the low-energy antiproton ring, in 1995. Then in 2002, Athena and ATRAP, two separate experiments, both at CERN, created thousands of cold anti-hydrogen atoms. Basically, the temperature of the anti-hydrogen, the velocities were low enough that we could perceivably capture them. In 2010, 8 years later, the first trapped anti-hydrogen was made at the Alpha experiment. And then in 2011, we essentially learned how to trap anti-hydrogen for an infinite amount of time. And we trapped them for 1,000 seconds because after 15 minutes, essentially somebody got bored and they turned the magnet off. So, now today we can trap them for 16 hours, 24 hours, however long you would like to. In 2014, the Alpha 2 experiment, where I work, finally went online. And since 2009 up to the last time CERN was still running in 2018 with the antiproton beam, we have been accumulating and trapping anti-hydrogen, doing experiments on them. And each year we basically improve our ability to trap. So initially we started off with one anti-hydrogen atom trapped every 10 attempts and in a given hour, and now we have about 1,000 anti-hydrogen atoms trapped in an hour. So once you have anti-hydrogen trapped, you can finally start doing studies on them and comparing them with results from hydrogen. So one thing we should know about hydrogen is that it has, a ground state, the energy level where where hydrogen is the most relaxed, but you can also excite the hydrogen with a photon to what we call the 1s-2s transition. It goes to an excited state, and this energy difference is known very precisely in physics. We know this to 15 decimal places, essentially. So in 2016, we did the result. We did a measurement to see whether the result for anti-hydrogen matches the result for hydrogen. Essentially, is the transition frequency between the ground state of anti-hydrogen to the excited state, is it the same for hydrogen? And we were only able to take 2 points in this curve, when our laser frequency is very far off and when our frequency is exactly at the value that we expect for hydrogen. And you can see over in this plot the results that our results for anti-hydrogen overlap really well and with the prediction and the simulations that we did. So essentially, we couldn't find a difference in 2016 between hydrogen and anti-hydrogen and their ground state and excited state frequencies. In 2017, we improved our results. We took a lot of points on this curve, and essentially within the error bars, we found no difference. But there's still a lot of room for improvement in these results. This result was a big breakthrough. We published in the journal Nature, which was a big achievement. And I was also, there was a lot of media coverage also. In a breakthrough experiment, scientists shine light on antimatter. That's our spokesperson, Jeffrey Hangst. And you can see a lot of vacuum equipment in the background. I was also featured in a Pakistani newspaper, a Pakistani physicist, part of CERN team that made breakthrough discovery on antimatter. But where does this leave us today? I mean, we've studied antimatter, we've studied hydrogen, we've studied its ground state and excited state. We've trapped it, and we've created an atom that does not exist in nature. It's something that we've only created in the lab. We've also had the first glimpse inside an antimatter atom. We've seen its energy states. But the question about the missing antimatter, it's still gone. We still don't know where is all the antimatter in the universe. We've seen no difference between the anti-world and the normal world so far. Nothing that's that can explain the massive difference that we observe in the universe. And the search still continues. But we're also doing another experiment now. Since 2018, we've been commissioning a new experiment, which we call Alpha G. And the G stands for gravity. And we have an interest in studying the gravitational relationship between matter and antimatter. So on the planet Earth, where we live today, we know that an atom of hydrogen essentially falls on the planet, just like a tennis ball. And if we had an anti-Earth somewhere out there, an anti-hydrogen atom would also fall because of the laws of symmetry that we have. But what we don't know and what we don't have a good theory for is that if you have an anti-hydrogen, antimatter particle on a matter Earth, is it going to fall, or is it going to rise up, or is it going to stay where it is? We don't know, and we must do an experiment to find out. So we're building AlphaG, and it's a very conceptually very simple experiment. Just like in Alpha-2, you create and you trap anti-hydrogen atoms, but this time you do it in a vertical trap. And then you slowly release the atoms. You observe where the annihilation distribution happens. And so when you release these anti-atoms, or they will have certain velocity. Some of them will go up, some of them will go down. But if the dominant is going down, then maybe we can say that, okay, antihydrogen is behaving more or less like a hydrogen. But if most of the atoms start going up, and you were expecting, half-half, or you were expecting something that conforms with gravity, then we would have a result different from normal hydrogen. And then we will have to definitely spend a lot of time analyzing our results and understanding, did we do something wrong, or is this a real effect? And if there is a real effect, and anti-hydrogen does go up instead of going down, then I'm sure somebody in our group is going to get the Nobel Prize. Fingers crossed. So AlphaG was almost ready in 2018, but CERN went into shutdown mode. So CERN operates on 5-year cycles, 5 years on, 2 years off, 5 years on, 2 years off. And the purpose of the 2 years is essentially to make upgrades and to install new apparatus. And so we couldn't collect enough data to detect anti-hydrogen production and do an anti-hydrogen gravity study. But since 2018, we haven't just been sitting idling around. We've really made a lot of upgrades. The AlphaG experiment is almost ready, and we're going to get beam in exactly 1 month and a day, so 23rd of August this year. And so we're really excited and really looking forward to doing antimatter gravity experiments. Hoping that we'll be ready by then. I hope so. But data collection takes some time, so you might hear from us sometime next year. If antimatter goes up, maybe a bit longer for the results to get published. But I want to go back now to my original question in the very beginning, where you saw the minions being excited by bananas. So what's in a banana? Banana contains potassium atoms. And an average banana contains about 450 milligrams of potassium. There are 3 naturally occurring isotopes of potassium, potassium 39, 40, and 41. And for naturally occurring potassium, about 117 parts per million is potassium 40, which is radioactive. It is unstable and has a half-life of about 10 to the 16 seconds. So if you do the math, you get about 1 out of every 100,000 decays of potassium 40 produces positrons. And effectively, you can say that bananas have potassiums, and from potassium, you get antimatter. You get the positron particles. Again, this minion is going to help us do the math. 1 banana, 450 milligrams of potassium, which is equal to 10 to the 21 atoms, which is about 10 to the 17 atoms of potassium 40, which is about 21 decays of potassium 40 per second. And in about 81 minutes, you produce 1 particle of antimatter from 1 banana. So during about a 1-hour lecture, you get about 1 positron emitted by a banana. So the next time somebody asks, what's the antimatter with you? You can tell them that you're going bananas. Thank you.
Thank you. Thank you very much. That was fantastic. I'm now terrified of bananas, though, so thanks very much for that. That's really good. As always, we will now take a 15-minute break, which means we will be back at 7:45 for the questions and answers. If you'd like to put some more questions in the Slido, please go to SitP-O skeptics.online/ask, and we will be back at 7:45. And once again, would you all please thank Dr. Sameed Muhammad for a fantastic, if somewhat terrifying, talk about bananas. Thank you very much. And welcome back. I hope you all had a pleasant break, got your filled your glasses, done what you needed to do, and we're back to answer some questions now that have been asked by yourselves over in the Slido. First question comes from Igor, and we have the question: do you have a favourite antimatter related wild theory? Mirror dimensions, parallel 11-dimensional worlds, flying frogs, anything really?
I do have a theory. I do have a favorite theory that many other people have talked about because it feels maybe possible, but maybe not. And that's the idea that antimatter is gravitationally repulsive to normal matter. So there is actually maybe equal amounts of matter and antimatter, but it's just not part of our visible universe. It's just so far away that it's no longer accessible. How the dynamics of that would work out, I don't really know. It feels a bit far-fetched, but still something fun to think about and consider. Anything more wild than that, I haven't really come across. Yeah, I think that's the only one that I feel like, okay, if there is any far-fetched chance of something like that happening, I think this will be really exciting.
Is that not something that you'd be able to have detected by now if there was some gravitational weirdness going on?
So that's the excellent question, and the reason we haven't been able to find out. I mean, we have actually a study of antimatter gravity from our old days where we trapped antihydrogen, but the error bar on the result is from minus 55 times gravity to plus 110. So it's like there's gravitational strength, and then you multiply that by 110, and it could be anywhere between minus 55 and 110 times the gravity. So essentially, we don't know. That was the answer. Yeah.
that needs a little bit more work on then, I think, if you're going to get those error bars down a little bit more on that one.
But this is a really, really interesting question, because the challenge here is that with antimatter, with charged antimatter particles like positrons and antiprotons, I mean, we can hold them for as long as we want, and we can study them. The issue is that we have to understand our particles through electronics, and electronics introduces electronic noise. And when you have electronic noise, you're essentially like wiggling your particles all the time. And when you're wiggling, you're basically damping out any signature of gravity on these particles. So you basically flood out any signal that you would have known for positrons or antiprotons, because they're charged. So the only thing to actually do is study neutral particles, because they're not wiggled by the electronic noise. They just behave like neutral particles. And we just need to now collect enough data, enough statistics in a vertical trap that we know and understand and is well built. That's why we're actually putting money into building this rather than using the old setup, which is not meant for gravity measurements. And hopefully in a year, 2 years, let's see.
Well, come back and let us know anyway. Next question is also from Igor. We've got: is it only matter and antimatter? Can there be something else in this relationship? Neutron matter or something halfway between? Or
That's a good question, and I think I don't specifically have a theory to rule out something else. Just like back in the day when the muon was discovered, it was a particle nobody was expecting. It was like, people just knew about electrons, and they're like, oh, suddenly you discover the muon accidentally, and I forgot who was the famous physicist, but he said, like, who ordered that? Like, where did that come from? So we could have a situation where you have essentially a third type of thing out there, but then of course it's going to completely destroy our current theoretical framework, and we have to invent a new one to understand where a new type of particle could fit in, a new type of interaction could fit in, essentially. So yeah, I can't rule it out, but it would be really nice to know.
There'd be Nobel Prize going if that was found, I'm guessing.
Absolutely. I think nowadays the challenge is to find new particles and to come up with new things. You can't just do an experiment, with a few people. You have to have huge, massive experiments. And then the question becomes, who's going to get the Nobel Prize? So, tough days.
issues with the Nobel Prize around that. Next question comes from Dimitri. If something went wrong during the antimatter creation, is it possible that the whole world would collapse, or possibly just part of it?
I think to answer that question, we should understand the quantities of antimatter we're talking about. So when we produce antimatter in any experiment, or even, for example, antimatter that's produced by, energetic particles coming from outer space and going through our planet or going through our system, you produce a handful of antimatter particles, or 100 or 1,000, or maybe at CERN where you produce a lot, it's like, 30 million antiprotons. But if you just look at 1 gram of particles, or like Avogadro's number of particles, it's 10 to the 21. So in comparison, it's nothing. And if all of the antimatter we produced since the beginning of experiments, since the beginning of science, if they were all to annihilate together in a cup of coffee, they wouldn't even warm it by 1 Celsius.
Oh.
So
what?
It's literally hardly any energy. It's a lot of particles, but almost no energy.
Anytime I'm talking to particle physicists, your use of numbers just blows my mind in every possible direction. You got massive numbers and tiny numbers, and it's just weird and confusing. So let's move to the next question then. How do you transport antimatter?
This is the new thing now at CERN is transporting antimatter. You can transport antimatter, and there are actually 2 experiments at CERN that have been approved to transport antimatter from one facility, from the antiproton decelerator where we currently have experiments, to a more quieter place where you can do more precise measurements on antimatter. Or in another case, so the first experiment is the base STEP experiment. And what the base experiment does is they trap antiprotons, and then they probe its properties, like the mass and the charge, very, very precisely, almost at the same precision, or sometimes even better than the precision of the proton, the matter counterpart. But they've currently hit a limit. In the facility, in the building that we are at, it's very, very noisy. You have all kinds of things like air conditioning and electronics, and even people walking. You can see that in the detectors. You can see people walking. So if you wanted to detect using antimatter, if somebody's entered your building, you can do that. It's an expensive way to do it, but you can definitely do that. So base STEP has decided that they're going to transport a few thousand antiprotons from the current facility. They're going to collect it. And how do they do that? Essentially the same idea, magnetic fields and electric fields. They're going to use a magnet, a solenoid, and they're going to have an electric field from electrodes inside the trap. The antiprotons are going to remain trapped. And as long as you do that, you have your system running on a truck. So you have to provide a battery-powered trap on a truck. You collect your antiprotons, and then you truck it to the other side of campus. And CERN, it's maybe like a 10-minute drive or a 15-minute drive to a new facility that they're building. It's going to be extremely quiet, and then they can set up their experiment and do it. This is let's say, the one purpose of transporting antimatter. And they have a design study. They have a grant from the European Commission to build this. So this is happening. We're going to transport antimatter. And then there's another experiment called PUMA, where they also want to transport antimatter, but they want to do it for nuclear physics. The idea is that we don't understand many, many things about nuclei. Nuclei are not just, spherical in shape. Sometimes they have elliptical shapes, or, ovoid shapes, and sometimes they have these neutrons and neutrons that are far away from the center of the nucleus. So there's some really, really funny things going on in nuclear physics. And in order to probe nuclei, they want to basically bring antiprotons from our antimatter factory to the nuclear physics factory, which is ISOLDA. A lot of nuclear physics studies are there. And then they're going to bombard the nuclei with antiprotons and let the antiprotons annihilate with the protons and the neutrons in the nucleus to see what is the arrangement of neutrons and protons inside the nucleus. And from the annihilations, they're going to detect, are they all symmetrical? Are they all is it a spherical nucleus? Is it like all the neutrons are on one side and the protons on the other side? And they also need to transport antimatter to be able to do that. They're a bit more ambitious in the sense that they need to transport about 1 million or 10 million or maybe even 100 million. And it's going to be very, very challenging to do that with the current technology that we have. Our magnets are not so strong. I mean, by strong, I mean it's like 5 Tesla or 3 Tesla. It's very strong compared to the magnetic field of the Earth. But we need to improve our material science, and we need to improve our ability to, hold antimatter without touching it even better, and to be able to transport it without causing the battery of the truck to go off or something. So it's going to happen hopefully soon, but it's a work in progress.
Sounds an incredible job. Next question. Is dark matter related to the antimatter? Is there a connection between the two?
I actually had a slide on this, but I'm not sure if I can share it. Let's see.
I'm sure our tech goblins will be able to help with that. There I am.
So is it transmitting now?
Yeah.
Cool. So I mentioned earlier, we have two families, the quarks and leptons. Unfortunately, dark matter doesn't live with these minions. It doesn't belong. It's an outlier. It's an outsider. And if you look at how dark matter forms part of our current universe, we essentially have about 25% dark matter, about 71%, 72% of something called dark energy, which we use to explain why the universe is expanding. And then what we call atoms, or, in our case, matter and antimatter. So atoms is only about 5% of what we actually know and understand really well in science, and the rest of the 95% is dark to us. And I mean, it's a cool way to basically tell somebody that I don't know. That's why we call it dark matter and dark energy. So it's outside of the antimatter and matter, the atomic world that we know of, and it is actually almost 5 times as big, and we have no clue. We have some indication that it exists from many, many experiments and observations of galaxies. But what is a dark matter particle? It's a question that remains unanswered at the moment.
Do you have any favorite possibilities? Are you in any camp or other, or do you leave that to others to worry about?
I think a lot of other people are worrying about it. There was supersymmetry. There is still supersymmetry as a possible idea, that there are some particles that are extremely heavy and don't interact, or extremely light that don't interact with our regular detectors. There are axions. There are sterile neutrinos. I mean, there's all sorts of particle theories and particle theorists who come up with ideas, but we haven't detected a particle that we can say, oh, that's a new particle, and that could be dark matter. I would say that if there is something to worry about, is that if there is dark matter out there, but we can't find it, we're in trouble, because the standard model of particle physics, the what we understand currently, I mean, it doesn't include dark matter, and if we don't find out soon, we'll be in the dark for a while.
Let's hope they get on with that then. Next question from Dave J. How does the universe exist? Shouldn't there be equal matter and antimatter from the Big Bang that then annihilated each other? What caused this 1 in a billion difference that Einstein was talking about?
Good question. If you know the answer, please do let me know as well.
There's another Nobel Prize for that one as well.
Absolutely. I mean, this is the big question. I mean, this is the whole reason the antimatter factory exists, right? We're trying to find, we're going through a whole list of properties that we know about regular matter, and we're trying to measure the same properties of antimatter. And maybe one or a few of these properties will tell us maybe there's a difference, and perhaps the difference is big enough to explain why in the universe we have so much more matter than antimatter. Because as the questioner said, there should be equal amounts. We should be annihilating all the time and re-popping out from the annihilations and annihilating all the time, But something happened in the beginning that we have no idea of, and we're trying to figure out. And a lot of research is going into it. Luckily, with some good applications, but the research is still ongoing.
Anonymous asked on a similar note, is there any experimental evidence to support this billion and one quote from Einstein and that might explain how matter came out to win that contest?
I don't think there is some evidence for the exact number, a billion. I've seen somewhere out there that it's 10 trillion and 10 trillion and one. I've seen 10 million. Well, the million one is a bit too low because we can rule that out because it's the difference is too big in that case. But really, I mean, if either, so there's only two possible, or at least there's two possibilities that we could think of. First is that they were created from the very beginning unequal. You just had more matter created than antimatter in some rare process at the time of the Big Bang that doesn't happen anymore. Or that even though they were created equally in the beginning, something happened along the way. Something caused antimatter to transform, a tiny amount of antimatter to transform into normal matter in a way that the other way around didn't work in the same way. And so if that's the case, then maybe we can measure a specific property that could explain, this difference. But we have to really look at all these properties and figure out which one it is or which ones combine to produce such a big difference.
Okay. A question again from Igor. What would it take to get to an antimatter-powered society? Is there some theoretical source of antimatter we could tap into to get over this small amounts problem that we're having?
Not yet. I mean, the antimatter is found even in the solar system somewhere, in some empty parts between the different planets, also in the Milky Way between different galaxies. But there is no antimatter galaxy that I know of, or even large or antimatter planet that I know of. Because if there was antimatter out there, antimatter and matter, there would have been an interface in between. And when there's an interface in between, there's always annihilations. And whenever there's annihilations, we can detect annihilations coming. We can see the light coming from outer space. So we haven't seen any large source of antimatter out there that we could tap into to build an antimatter society or even antimatter-powered society. But if such a system, were to come in a few billion years or a few million years, I mean, I'm not sure.
Okay. Gray the Earthling has a question now. Does Dirac's equation apply to photons as well? Do we have antiphotons, and are they particles of dark?
Yeah, that's a great question. So as far as I understand, and I'm an antimatter physicist, but not a particle physicist, so I could be a bit wrong here. Dirac equation doesn't apply directly to photons because photon is a boson, and things like positrons and electrons are fermions. But photons are essentially their own antiparticle. In some way, they don't interact with each other, so you don't see them annihilating in that sense. But basically, a lot of particles, also similarly for gluons are the particles that are inside the nuclei binding the quarks together. So they are also their own antiparticle. There is no dark photon, not that we know of.
Okay. Cleo asks, we've got positrons, so when will we get the first positronic brain like they have in iRobot or in Star Trek? They can exist, can't they? Would bananas help make them a real thing?
Absolutely. Just collect as much bananas as you can. I mean, I don't think so, but it's a good question.
We'll leave that one to the science fiction rather than the scientists then for the time being. Gray the Earthling asks, are you sure that negative mass and energy are unphysical? How do you know?
I don't know. So there are some theories out there, actually even some experiments that are looking for particles with a negative mass. Now, don't ask me how they do it or what they're looking for or what signatures that they can look at. But if you search online, there are some experiments for searching for negative mass particles. Yeah, the theory is beyond me. So I don't know. But yeah, am I sure? Absolutely not. But are there negative mass particles unphysical for now until we find them.
Okay. Stephen Aspinall asks, is there an antimatter universe where they're currently wondering where's all the matter? And does that account for our dark matter plus some miscalculations?
I think the first part, is there an antimatter universe, is similar to the idea, the wild theory that we have, that all the antimatter is some far off corner of the universe, no longer observable, and maybe there's an antimatter society there with antimatter scientists looking for where's all the matter gone. That's the only science fiction plausible, not sure kind of theory that could account for this discrepancy. Nobody's come up with a very good mathematical model to explain this. So again, it's standing on really shaky ground. But that's a scenario that I could imagine as as a person who's really, really creative, I guess. But would it account for dark matter? Probably not, because there seems to be a lot more dark matter and dark matter effects than antimatter. So there is something out there which is still dark.
And isn't it the case that the dark matter we know that it's fairly close to us and it's in our galaxies and it's all around us?
Absolutely. We see the signatures of dark matter all the time from gravitational effects. So yeah, or some other theory to explain it, but antimatter alone would not be sufficient to explain that.
And also, this is a question just from me. If we were in an antimatter universe, we wouldn't know it anyway, would we? We would think we were in a matter universe.
Yeah, so I think that's a question of calling something positive or negative, right? When the electron was first discovered, why did we assign it a negative charge? We could have assigned it a positive charge, and all the electricity today would be, negative, going from negative to positive or something like that. So it's a convention that we chose. It's essentially choosing us to define something as positive or negative, or what we call up. We could have called that down and this up, and it would have been the same.
Okay. Dave J asks, how would anti-hydrogen interact with something like oxygen?
That's an awesome question. Anti-hydrogen. So essentially, all the interactions don't happen at the molecular scale. They're happening at the particle scale. So anti-hydrogen, essentially, you have the antiproton, which is essentially anti-up quarks and anti-down quarks, and then you have the positron. In the oxygen, the matter oxygen atom or molecule, you have protons and neutrons, which again has quarks inside it. So you have, up quarks and down quarks. And essentially the anti-up quark from the anti-hydrogen and the up quark from the oxygen would annihilate. The anti-down would annihilate with the down quark, and the positron would annihilate with the electron. That's how the annihilations would happen. And when they will annihilate. So even though they're different, the fundamental constituent particles are the exact opposites, and then they will interact that way.
So you'd be left with what's ever left over from the oxygen, whatever's not paired up in the... Exactly. Anonymous asks a question related to a previous question. Do any of the gauge bosons have antiparticles?
Yeah, so I mean,
First of all,
I guess...
Sorry, can I interrupt first? Obviously, everyone understands what a gauge boson is, but just in case, could you explain that for us, please?
Okay, so gauge bosons are particles that mediate the force. So maybe I can try to explain what a gauge boson is. We have particles, like electrons and protons that I've talked about, but we also have forces like the electromagnetic force, or the weak force, or the strong force. The electromagnetic force is essentially the force that allows a negative and a positive particle to attract each other, or two negative particles to repel each other. And they're mediated by a photon. The photon is the carrier of the force between these particles. Then similarly, you have a weak force. It kind of shows how, in a simple way, how nuclear decay happens. How do unstable nuclei decay into other nuclei and emit some particles. And these interactions are mediated by the weak force. The weak force has something called W boson and Z boson. So a W plus and a W minus, they're let's say the opposite or the anti of each other. And then you have the Z boson, which has no charge. It's a bit complicated because each each force is mediated by another particle, and not all of them are antiparticles of each other. So you have the gluon for the strong force, the Z and W bosons for the weak force, and the photons for the electromagnetic force. And in some of the cases, they're the antimatter anti of themselves, or they have a W plus and a W minus. And I mean, again, caveat, I'm not the expert in gauge bosons, so you'll have to study some quantum field theory to get a more good answer on that.
Yeah, study quantum field theory at your own peril. The next question is from Anonymous. Will we ever be in a position where we can start doing anti-chemical reactions?
Aha, that's also something really cool. As you've seen from my talk, we've only been working on anti-hydrogen so far, and as much as we love anti-hydrogen, we really want to get to a point where we can go to the next atom, which would be anti-helium, right? So you have in hydrogen, you just have a proton in the nucleus, antiproton in the nucleus. Very easy to very very easy to hold with electromagnetic fields because it's charged. You bring in an anti-neutron, it's neutral. We don't know how to trap it, and we can produce it probably from collisions of high energy collisions and particle accelerators, but there is no particular way to trap it. So until we come up with a clever way to cool down and trap antineutrons and mix them with antiprotons to make a nucleus of antihelium, we haven't gone down the periodic table yet. So we're still at the very first atom of the periodic table, and it will take maybe many decades to get to the second one. But as soon as we have that breakthrough, as soon as we have the ability to play around with antineutrons, then maybe there's no stopping. People will start adding like, oh, third one, whoa, let's make antioxygen. Oh, let's burn antihydrogen with antioxygen and make some anti-fire or something like that.
So that's maybe we shouldn't go down quite that route. That's a bit terrifying for my taste. Dave the drummer asks, is there a way we could detect antimatter in our galaxy or outside the galaxy in the intergalactic space, perhaps?
There are some experiments that are on the International Space Station. One of the experiments is called alpha magnetic spectrometer. And what it's trying to find, among other things, is what we call primordial antimatter. Antimatter that's not something that was produced from cosmic collisions, but something that is around from way early, close to the time of the Big Bang. So if there is an antimatter particle whizzing around the universe and just by chance happens to pass through the detectors of the alpha magnetic spectrometer experiment and leaves a trace that has an energy signal that's so different from what we have normally, we would be able to detect an outer space, intergalactic particle of antimatter. So far, no signatures yet, as far as I remember. But once that happens, I think it will be pretty cool to actually find antimatter that was not produced as a result of something that happened recently, but something that's been there for a long time.
A deeply fundamental part of the universe, rather than being this Johnny-come-lately. Anonymous asks, is it possible that there are regions of antimatter and matter without gravitational repulsion being necessary?
I would have to think of a scenario where the antimatter would then have a different kind of an interaction with regular matter. So not your electromagnet or weak force or strong force or even gravitational force, but a fifth force that somehow allowed it to be in a certain part of the universe that's no longer observable, or something that happened to it and maybe it comes back into existence. Maybe another dimension. Somehow antimatter goes into a different dimension, comes out. So there's creative ways you can come up with to put all the missing antimatter, but then you have to prove that creative way actually works, and you have to come up with an experiment. So yeah, I mean, it could be a multiverse theory where all the antimatter somehow got absorbed in a different universe, and then maybe that universe is going to merge back with our universe in the future. But again, there is no currently a way to test the multiverse theory. We would love to find out where the antimatter is, but that's not something viable at the point with that theory.
Coming up with the experiment is quite often the really hard part.
Yeah.
Anonymous would like to know, surely all anti-hydrogen is expected to go up. After all, normal hydrogen does.
Okay, normal hydrogen goes up because normal hydrogen gas, I have to be precise here, goes up when we are inside an atmosphere of oxygen and nitrogen. So we're surrounded by air, right? And air is oxygen and nitrogen. And hydrogen gas goes up because it's lighter than oxygen and nitrogen. But our experiments are in vacuum. Inside a vacuum, if you have a molecule of hydrogen gas or even an atom of hydrogen, it will go down because there's nothing else pushing it up. And so we know, for example, in a vacuum chamber, hydrogen does go down. And similarly for anti-hydrogen, we can do an experiment to see whether it goes down or goes up. So yeah, hydrogen gas would go up inside our current atmosphere of nitrogen and oxygen, but in a vacuum, it goes down.
Question from Neil, which obviously I understand entirely, and I'm not just reading it out, but I assume you'll understand. Do you ever worry you might cause a resonance cascade? And again, I understand what that is, but if you'd be kind enough to explain to other people what a resonance cascade might be.
I actually don't know what a resonance cascade is.
Okay, apologies for that. We'll move on to the next question then, I guess. Okay, and this is our final question, and it comes from Skeptical Gumby, and actually from a worrying number of the people in our Slido today. So I don't know what that says about our group, but how many bananas would you need to build an antimatter bomb? Asking for a friend, obviously.
Okay, I guess if you're asking for a friend, I can tell you. So as I mentioned, it takes about, a banana, let's round it up. 1 kilogram of banana produces one positron every 80 minutes. So maybe if you want to make an antimatter bomb fairly quickly, you would need about 10 to the 23, 10 to the 24 bananas in about if you want to make an antimatter bomb in about 2 hours, you need 10 to the 24 bananas. Not so much. I mean, you can probably is more atoms than the universe.
Also, there is the problem at the moment that Tesco's is very slowly stocked of bananas, so we do have that problem.
Oh, that's unfortunate. Well, you could call up Tesco and make an order so that they start stocking up now, I guess.
We'd like to order 10 to the 24 bananas, please, for delivery. Okay, that's the end of our talk for today and our end of our question session. So once again, I'd like to ask everyone in the chat to show their appreciation, please, for Dr. Sameed Muhammed. And to remember that we are back in a fortnight time for our next talk. Keep checking the website and the Facebook group to find out the details of that. I'm looking in the chat and I'm seeing, apparently Resonance Cascade is a Half-Life reference, which is why it went way over my head. But once again, I'd like to thank Dr. Sameed Muhammed, please. And thank you very much for a wonderful talk. Fascinating.
Thank you so much, James, and thank you so much for the crowd for your amazing questions. It was really a pleasure to talk about antimatter, and please, if you want, you can get in touch with me on LinkedIn or Facebook. Initially, I was a bit skeptical, but skeptical. So you could you could get in touch, and I can respond to more questions if you would like.
Thank you very much.